Hi, everybody. If you haven't gotten these notes in class about complex circuits, they start with something that looks kind of like that. Sorry for the fuzziness there. You want to go on to the Mustang Physics website and print them out real quick. About 4 pages worth of information. Got some circuits in here we're going to take a look at, and you want to make sure you have those in front of you. So if you don't, press pause and go grab them. All right, the magic technology. You paused it, you printed it, now you got it. Let's take a look at this. So when we say complex circuits, all we simply mean is that it's not series and it's not purely parallel. So let's take this first example circuit here. We've got 2 batteries, and that's going to drive current through resistor 1 and through resistor 2. But at this junction, we could write a junction rule equation that the total current into that junction would be equal to the currents flowing out. The currents flowing out we'd call I3 and I4 because one part of that current goes through resistor 3, the other through resistor 4. Once either of those currents get through resistor 3 or 4, back to the battery, which is the place where it was going to flow anyway, take the path of least resistance right through the wire. Now, all the things we know about purely series and purely parallel circuits apply to this circuit, and we just have to be careful not to overgeneralize. For instance, if we think about this section here, that's purely parallel, which would mean if we hooked up a voltmeter here and here, it'd be the same as hooking up a voltmeter here and here, since there's no potential difference between these two places, and there's no potential difference between these places. So the voltage we'd read across resistor 3 and resistor 4 are the same as each other, but importantly, we can't overgeneralize and say that it's the same as the total voltage, because the total voltage would be measured between here and here, and some voltage would have to be lost across this resistor, and some voltage would have to be lost across this resistor. So only the remaining voltage would be dropped across resistor 3 or 4. If you think about this from a loop rule perspective, the voltage gained across the battery here would be lost across resistor 1 and 2 or 3, or that voltage gained across the battery would be lost across resistor 1 and 2 or 4. So it's going to be one of those two paths through the circuit. So the total voltage is equal to the voltage across 1, 2, and 3, or it's equal to the voltage across 1, 2, and 4, because the current has only those two loops that it could pass through, and all the voltage gained across the battery must be lost across the resistors in whichever path the current takes. Now we'll get to this. Trying to boil this all down to one resistance equation in one step actually ends up being more trouble than it's worth oftentimes. So we'll take a look at how to break that down in smaller chunks later. So let's go onto the PhET website and let's take a look at a circuit that looks just like this. You can keep your notes in front of you, but as we take a look on the PhET website, what we'll see is I've got a resistor here at where resistor 1 is, another one where resistor 2 is, another where resistor 3 is, and resistor 4. And if I close the switch, current will start to flow. I've got 2 9-volt batteries, so if I measure the voltage across the 2 cells together, those add up to 18 volts. And if I measure the current coming out of the battery, 0.4 amps, and that remains 0.4 amps through resistor 1, through resistor 2, and stops being 0.4 amps at that junction because some of the current would go one way and some of the current would go the other. Notice that the current through 3 and the current through 4 add up to the same as the total, so that's just the junction rule applied to that spot. Also notice that if the resistance of each of these paths were different, that affects the total current, and it affects how the current is split. More of the total current goes through the path of least resistance, although not all of it, because otherwise that would make that path greater resistance. Some of the current will take any possible path as long as the resistance is reasonable. Now, the voltage lost across resistor 1 looks about to be about 7.4. We'll just kind of round it there, and we'll ignore the positives and negatives. That just has to do with which side of the meter we put on which side of the resistor. That's about 3. 10.7 there. So what are we up to? About 10.1, and we measure the resistance of that, 6.9, add that in. Hey, look at that. We're up to the 18 volts. And of course, this 6.94 volts we're measuring across this resistor is exactly equal to that voltage here, because again, the potential difference between this spot and the wire is 0 as long as we're idealizing the wire. So any two resistors wired in parallel have the same voltage applied to them, but if they are in series with some other chunk of the circuit, while they get the same voltage as each other, they do not have the full voltage of the battery applied to them. So complex circuits have to be broken down into chunks, and we can think about this as a parallel chunk. And then once we simplified this into one resistor, we could think about it as a series circuit. All right, let's take a look at the bottom one on that first slide now. So going back to the notes, let's take a look at this one. So here you can see we've got three resistors in series, R2, R3, and R4. And they're in parallel to one resistor, R1. So you can think about the loop equation again. Kirchhoff's loop rule says we gain some voltage across the battery, got to lose it as we go through any loop back to where we started. Well, one of those loops would just be through resistor 1. That means the voltage I'd measure from here to here would be VT. So the voltage Vs that's labeled in the diagram would be equal to V1. This resistor would function just like it was the only resistor in a circuit, because the current that flows through it flows only through it. However, a different amount of current could flow through R2, then R3, then R4, and then back to the battery, which means the voltage dropped across all three of those would have to add up to the voltage supplied by the battery. Now, since those resistors are in series, the current through each one of them is the same. But importantly, again, we can't overgeneralize. That's not all of the current. We can't forget that some of the current is going to go through resistor 1, and that current would never go through resistor 2, resistor 3, or resistor 4. So the total current then is I1 plus either I2, or I1 and I3, or I1 and I4, since the current through resistor 2, 3, and 4 are the same. And again, we'll worry about how to break that down into one equation for the resistance a little bit later in the notes. So let's take a look at this circuit in FET. I've got it pre-built right here. So here's resistor 1 in parallel, and then resistors 2, 3, and 4 in series to each other, but in parallel to resistor 1. So again, when we close the switch, current can flow, and the current through resistor 2, 0.4 amps, is also the current through resistor 3 and is also the current through resistor 4 since they're in series. But that is not the total current, because the total current includes the current flowing through resistor 1, which is on a separate path. Now, the voltage across resistor 1 is the same as the 18 volts applied by the batteries, because for the current flowing through that loop, that's the only resistor, so that'll be the only voltage drop in the circuit. And if you notice, that measurement is also the voltage across resistors 2, 3, and 4 together. So if we measure the voltage drop across each one of them individually, we'll just get a portion. 8 volts to this resistor, 6 volts to this resistor, that's 14, and 4 volts to that resistor, there's our final 4, so there's 18 volts dropped across the 3 resistors. And just like we saw in the series parallel lab, in series, the resistor with the greatest resistance has applied to it the most amount of voltage that's shared between the series resistors. The lowest value resistor gets the lowest share of the voltage, since the voltage will be applied to wherever there is resistance in the circuit. So being able to think about how the current will flow in the circuit and where voltage will be dropped in the circuit, depending on not just the value of the resistors, but also how those resistors are wired, is the key to thinking through how these circuits are going to function. Even though they're a mix of series and parallel circuits, we can still think about each chunk as a purely parallel or purely series chunk. So let's go back to the notes again and press forward a little bit and see what we can do with this kind of thinking. So one thing that we can do is recognize that if we do have purely series or purely parallel chunks, we can use the equations that we know relate the resistance of each one of the resistors to the equivalent resistance of that chunk. Remember that in parallel, it doesn't add up because each resistor in parallel, if you kind of think about the physical dimensions of the resistor, it has a certain length and it has a certain cross-sectional area, and depending on what it's made out of, it's got a certain rho. So if we add another resistor in parallel, from the current's perspective, there's more cross-sectional area. So more resistors in parallel. Remember, resistance is rho L over A. So if area increases, as it does if resistors are wired in parallel, there's more total cross-sectional area for current to flow through. That is on the denominator of the fraction, which tells you that the relationship between the area of the resistors and the resistance of this chunk is actually inverse. So more resistors in parallel leads to a smaller total resistance, and that's what this equation predicts because that's what it's modeled after. So being able to replace a chunk of circuits that are in series or parallel with an equivalent resistor is actually one of the strategies we can use to simplify a complex circuit to predict how it'll work.